I cannot do blood, so not that kind of doctor, not that future for me. I like rocks. You can bang them up; they don't bleed.
Please welcome the incredible VolcanoDoc in here with us today. VolcanoDoc, if y'all did not know, PhD in volcanology, degree in geology as well. She is a real life scientist and professor, doctor to sick volcanoes, as we like to call her here on the show. She's also a Twitch streamer and science communicator and educator. On top of that, she's given seminars and lectures and posters, not just at TwitchCon on innovating in science on the platform, but at other real life scientific conferences. She is probably one of the best people I know and advocates for all things science. So, VolcanoDoc, thank you so much for coming on the show for our Women in STEM month.
Well, thank you. I really appreciate you inviting me, and I'm so sorry that I couldn't do it before now. Uh,
We just had to be ready
you,
for season two. That's what it was.
yeah, yeah, exactly,
So,
exactly. I
VolcanoDoc, if you wouldn't mind giving us just a quick introduction on who you are now and just a little brief introduction.
Okay. Well, hi everybody. My name is VolcanoDoc. I am a doctor to sick volcanoes, as Dr. Blint so eloquently puts it. Uh, but I'm a professor. So I'm an assistant professor of mineralogy and petrology at a university in the Midwest. And what that means is that I am hired to teach students the foundations of geology about rocks and minerals and how they form, why they're important, how to identify them, the theory behind them, and things like that. And then, as a professor, which if you guys didn't know, I actually didn't know this until I became a professor. 40% of my job is to teach, 40% of my job is to do research, and then 20% of my job is to do service, like serving on master students committees, doing things with the university, or doing science outreach, like my weekly Twitch stream. So that all kind of like lumps in together, and that's what a professor is. So as for my research, I'm a volcanologist. I use mineral chemistry and lava chemistry to try to understand how and where magma is stored beneath active volcanoes, with implications for eruption triggering mechanisms. And I focus on, well, right now Cascade volcanoes, but typically volcanoes in the western United States. Yeah, that's me in a nutshell right now.
So I have a lot of questions on just, what even some of those words mean. But I want to take us back, Doc, because it's one of those things like, when did you know, I guess, number one, that you were interested in science, right, as a potential career trajectory? And two, was that at the same time that you were interested in volcanoes, or did that come later on?
Ooh, I've always been into science, even as a kid. I did science Olympiad. I went to nerd camp. I was a super nerdy science kid. Loved every second of it. But I never really even knew that geology was a thing. When I was in high school, I wanted to be a forensic pathologist, and be like Bones, on the TV show. I cannot do blood, so not that kind of doctor, not that future for me. I like rocks. You can bang them up; they don't bleed. Uh, but then I actually ended up dropping out of high school because I got pregnant. And so I got my GED. I'm actually a high school dropout, despite the fact that I am a doctor. I did not finish high school, so it's never, ever, ever too late. Just to put that out there. And then so I got my GED, went to community college, and I had gotten a job as a paralegal at the time. Uh, I was doing bankruptcy and personal injury law and family law and stuff like that. I really liked it. And I figured, like, okay, well, this is easy enough. Like, I can make a living doing this. Like, I'll just do this. So I got my associate's degree in paralegal technology, transferred to the local 4-year school, and I had my heart set on being an environmental lawyer. So I wanted to go to Lewis and Clark and do environmental law. Work for the EPA and be a sick Aaron Brockovich style lawyer, as it were. But then I got sidetracked uh, because I took this class. I ended up being an environmental science major, just with the intention on going to law school later on. And I took this class called the Archaeology of Ancient Disasters. So Melissa in Denial would have loved this class. She really would have. It was such a cool class. I learned all about how volcanoes and earthquakes have really, like, these big disasters have impacted the course of human history. And it was just so phenomenal to learn all about that interaction. And I remember we watched a YouTube video with, I'm not sure who, but it was one of the volcanologists in the silver suit. And I was just like, I had no idea that that could be a thing. Right. And so I raised my hand and I was like, how do you do that? Like, you can do this? What is this? And the professor said that you had to go get a PhD in volcanology, work for the USGS or a volcano monitoring survey. And that's how you could get that job. Uh, that is not the route that I have ended up going. But I do know people. I have colleagues that work for the Hawaiian Volcano Observatory. I have a co-author on a poster who, like, literally their job is when Kilauea's fountain goes so high, they stand on the caldera rim with nets to catch the tephra as it quenches through the air, so that it's completely uncontaminated and perfect for geochemical analysis, right? So, like, that's the best job ever. That's the dream. But was not to be. So I was able to get into grad school. I got my master's in geology and then ended up getting into a PhD program. So I have my PhD now in earth science with the emphasis in volcanology and igneous petrology. Petrology is the study of how rocks form. So I study how igneous rocks form from a magma. And yeah, so I did a postdoc work on I didn't do a formal postdoc. I finished my PhD literally like a month before the biggest eruption in the past century. And I was able to kind of make my name on a couple papers for that eruption, which was very nice. And that was my informal postdoc work. Uh, we moved up, so my family and I moved up to Washington State for my husband's job. And it's really nice because I get to be around active volcanoes. But I was lucky enough then to get a job as a tenure-track professor, which, if you're not familiar with the academic job market, is like, it's like getting into the NFL. Literally, you have about the same chances to get now in 2026. You have about the same chances of landing a tenure track position as you do getting into the NFL. Like, it's rough, and you do what you can to get that job. You know, NFL players have to move for their jobs. Academics and professors, we do too. So I left my family behind, not behind, but we are doing the long distance thing right now while I am carving out my niche as a professor and hoping to get tenure. And that's how we got here.
So VolcanoDoc, there's so many elements of that story that I want to kind of dig into, but I like how you said that it's the NFL that essentially that you were able to pull off, right? In order to get this professor position, because when you told us the start of this journey, you were like, I didn't get my high school diploma, right?
I
And
didn't.
you're now in the big leagues, as it were, as a professor. Can you
I mean, it's like I like play for the Jets, but it's in the big leagues.
it's still the big leagues. Could you kind of talk to people about that experience? Like, do you feel like you were any at all at any disadvantage of going an alternate route in order to get a GED and then go into those particular studies? Like, is it because it kind of gives a story of that it's never too late, right? In order to follow your dreams of learning and becoming a scientist. And I guess what difficulties or did you feel like you were at any disadvantage of going down that route? What advice would you give to someone who's thinking about something similar?
Oh, I faced a lot of disadvantages. So what I didn't mean to leave out of that story, because she is absolutely the most important thing in my life, is the reason I dropped out of high school is because I got pregnant. And so I had my daughter right around right before I turned 18. And yeah, so I was a teen mom, single mom, and I did that. I worked full time, went to school part time, raised my kid. I had zero social life. And I was very lucky that even though I'm not close with my family, they did care for for their granddaughter, so they were willing to help me out by spending some time with her, especially like when I needed to for class and things like that. So I'm very very thankful. I would not be able to get where I am today, without the help of my family, friends, especially a lot of friends who helped really helped me raise my daughter. It does truly take a village. I could not have gotten here on my own. Or even like an undergrad, I had a professor who he was the mineralogy petrology professor, and kind of inspired me to become who I am today. Uh, he would let me bring my daughter to class. Like if she had a snow day and I didn't, because the universities didn't shut down, but the K-12s did, you still have to go. But if you have a kid, what do you do? And as long as my daughter was well behaved, he didn't mind. He in fact would like incorporate volcano videos and stuff for her. It was really sweet of him. And kind of the same thing for I got very very lucky by being able to work with some really very great supportive advisors. Oh, Steph, good question. So my daughter was born. So I was 17 when I had my daughter. It literally took until she graduated high school. So this whole time, her entire life, I was doing college and grad school and everything. And I ended up getting my PhD the same year that she got her high school diploma, which is something that neither her dad or I were ever able to do. So
Did
very,
y'all
very proud of
did
that.
y'all take like both of y'all like cap and gowned up photos?
Oh, I didn't cap and gown up, but no, we took pictures. Her dad flew out and everything for her graduation, and we all took photos by the beach, and it was just a really really nice evening.
Nice. When you were in undergrad and you had that professor who was, kind of gave you that trajectory to go into volcanology, in undergrad, did you have any hands-on experience in kind of the field that you would get into, or is that something that you kind of only were able to experience upon your master's degree? Because a lot of times, right, when you're getting into these fields, that hands-on experience is set to be a really critical thing. Were you able to get any beforehand?
No, no, I didn't even see my first. So I'm originally from the Midwest. Like literally came back not to my hometown, but I came back to within driving distance of my hometown to teach. And I didn't see my first mountains until I think my junior year of college, like proper mountains, not like the Ozarks, because those don't count. Those are glorified hills. But like I didn't see my first proper mountains until like halfway through my undergrad, and that was only because I got to go to a conference. And then I started actually. I'm so thankful to geology. It because it's a field based science. You really, with some exceptions, there are people who study like remote sensing, people who do experiments and things like that. It is possible to be a geologist, and not go to the field. It is possible. So there are people who do work with limitations, but I got to travel to some really amazing places to do field work, and I wasn't even originally doing volcanoes. I was studying magma mixing, but like in magma chambers for in rocks called plutonic rocks, where that magma has never erupted. It's cooled and crystallized in situ or in place, and then ends up becoming a magma chamber. So, um, for anybody in chat who doesn't know this, liquid hot magma, not really a thing. Magma is usually stored cold and mushy. Like cold is, which is like I don't know, like 600 degrees centigrade. But it's mushy. It's like if you leave honey in the cupboard for too long. That's what a magma really is. And so if a magma gets to be more than about 55% crystalline, it becomes too viscous to erupt. And we say it dies a viscous death, right? It can never erupt and it's destined to become a granite. So I was studying these types of magmas that had never gotten erupted, still magmatic processes. But I was looking at these rocks called mafic enclaves, which happen when you have one type of magma come into a magma chamber that has a different type of magma in it. And my thesis advisor for my master's noticed that I was like really into this and noticing some really cool stuff. And he thought I might be able to better help out on a different project. And so I actually got to work at an active volcano for my master's degree. I worked in Lassen Volcanic National Park in Northern California. And I worked on a group of 6 lava domes. It's called chaos crags, trying to understand magma storage and eruption triggering mechanisms. And so for my master's, I tried to I figured out what triggered this actual eruption. And which was very illuminative because there's a lot of different things that can cause an eruption. So it's good to look at each volcano has had to see the different types of processes that it has over its lifespan and the different ways that it can end up having an eruption triggered. Um, and
So
so I ended up.
one question I have for you, Doc. Just I have a lot of questions actually about the process of like how to identify what caused the volcanic eruption. But when you were working on these magma storage locations, right, like for the start of your master's degree, for us at home, what does that look like? Like, what does that mean that you're working on these chambers, right? Because for us, some of us, it's like you see it in movies, and then there's just like no connection of like what does the field work look like? What kind of data are you getting? What is the dream data to get? How do you interpret it? What are you just in boots in the field and you're just digging, or in the lab, a bit of both? What does that look like?
Um, my undergrad asked me that very same question. It's a great question. So I am currently working with one undergraduate and my 2 graduate students on this problem right now at an active volcano in the United States. So we're trying to understand how and where, like how deep magma is stored beneath Newberry, which is a volcano in Central Oregon. It's active. It last erupted 1,300 years ago. And the last eruption was sizable. It was a 4, so smaller than Mount St. Helens, but in 1980, but still explosive. And then at the end, it produced this lava flow. So I take my students, we hike up the side of the lava flow, which, if any of you in chat are curious, Google big obsidian flow. That's where we work. Um, just like paleontologizing needs to get a permit when he does field work, I have to get a permit too. So I've been very fortunate that I was able to get my permit, get it secured. It's for multiple years, designed around this project. So I let the rangers know, like, hey, we're doing field work on these dates. Check in. That way they know that there's people out where people normally aren't in case we get hurt, because the chances of getting hurt are not small. Um, this is a obsidian lava flow, right? Obsidian's volcanic glass. It's sharp. So I went through a pair of like good leather gloves, like rose gardening gloves for roses, which are like really reinforced. I went through one pair in 2 days of field work. So you hike up the side of the lava flow, and then you scramble up onto the lava flow, and then you're like bouldering. So it's kind of like rock climbing, but you're not up high, but you're hanging onto the rock and kind of traversing for half a mile or so, and into the vent. And there's no active lava, no active eruption. We're just in the vent, the last stuff to come up out of it. And we're looking for special type of rock, which might help us to get a better idea, like this recharge, this stuff that came in, that mixed with the magmas that were already there and then the eruption happened. So we literally just like walk around the vent of the volcano. We're looking for stuff that isn't normal looking and check it. And if it looks like this type of magma that we're looking for, or maybe a bit of the crust underneath, like the continental crust underneath the volcano, that can come up, get ripped up by the lavas, or sorry, by the magmas as they come up, and that can get included too. So we're looking for all these types of things that just look really, really different, and documenting them. And if we find some that look a very certain way, then we might collect them. And so we collect them, take them back to the lab, crush them up. So we use a big jaw crusher, it goes, grinds them up, and then use a different like mills that will turn that rock into a powder, like very fine powder. Then that gets melted, turned into a glass bead, and we use X-ray fluorescence spectrometry to determine the chemical composition of the lavas. Uh, that's for, we use XRF. We also use ICP-MS, so inductively coupled plasma mass spectrometry, to look at some other types of elements. So I'll look at like majors, traces, and isotopes, usually just like elemental concentrations and then isotopes of the lavas that have come out. And so right now we're using that to kind of see if we can tell which ones might be more primitive and, excuse me, better represent the deeper parts of the plumbing system. So then once you kind of like get an idea of which rocks might be the best to tell you, to get this information from, then we take bits of the rock, grind them down super, super thin. So they're 0.03 millimeters thin. This is called a thin section. And in that, we can see textures in the lavas, the minerals in the lavas, and things like that. And then the next step that I will be helping my students to do is take those thin section slides. My students are going to characterize them, like kind of describe the minerals that they see, the mineral proportions, the textures that can kind of help us better to understand things like that happened inside of the magma chamber. We're going to take them to another university that has an electron microprobe, which is another type of instrument that we use to measure really tiny spots. Like you can measure different zones across a single crystal inside of a rock, like a microscopic crystal even. So really teeny tiny, like what Diatom's attack does. He has his SEM. We're talking on that small scale, like very, very small scales. And get the mineral compositions from that. And then there are a series of different equations that are used called thermobarometric equations, like thermo for thermometer, baro for barometer. And we use the chemistries of these minerals and glasses that represent the liquid parts of the magma at the time of the eruption. Using these equations, you can reconstruct really and kind of estimate the pressures and temperatures inside of the magma chamber that these crystals actually grew at. And so what I'm estimating here is, okay, how deep beneath the summit of this volcano did these crystals actually grow at? And that helps us to estimate depths to magma storage regions, if that makes sense. So that's literally what I do.
So what is the end game for that? You've made that estimate, right, of figuring out where these chambers are by this backwards movement, right, from the various minerals. What's the end game of that? What are we learning that's like really critical about you having to go
So
down into
glad you asked.
vents of magma? And I'm for the community, I'm obviously it's a loaded question, right? This is like what funding agencies ask of like the big thing of like, why is this important for us to do, not just with this particular site, but with many different sites around the world? Like, why is it that, right, VolcanoDoc's job is a critical component for just, survival, right? In the
It's
grand
a
scheme of
loaded
things.
question, but it's not that difficult of a question, actually.
Perfect.
So, chat, you would be very, very surprised to learn how few active volcanoes in the entire world are not even just adequately monitored, but monitored.
I
Um,
guess to
you know,
what is what if, in this answer, what do you define as adequate as well, right? Because that's gonna
well,
be
that's kind of a loaded question. I have a different opinion from other people. To me, I'm like, no, better safe than sorry. I want everything on it. Um, so usually you need like 3 seismometers, a couple gas, like gas sensors, temperature sensors, and things like that. But the reason why what I do is important is let's say there's an earthquake swarm, right? When magma moves through the Earth's crust, it breaks rock, right, to go through like this. So yeah, so when as it propagates forward, it moves through what's called a dike, and it breaks the rock in front of it as that dike moves forwards, and that rock breaking makes earthquakes, right? I There was a earthquake in Iceland that just ended last year, and in November 10th, 2023, when it started, there was like something like 13 million cubic meters of magma moved from a storage region 5 kilometers deep into this dike structure beneath this town, like literally overnight. It was absolutely terrifying. But there's videos that were posted of the earthquakes that were happening because the magma was moving upward. They're very unlike a normal earthquake, very, very different, very, very scary. So let's say now that those earthquakes can be used kind of to understand where magma is, right? So when magma moves into a volcano, you can get earthquakes. If you can figure out where the earthquakes are happening, that might, if the earthquakes are happening at the same depths that we know through petrology, my area of study using the minerals and melts and stuff, that hey, that's where magma is being stored. We also use geophysics, which is a whole different field. They use like seismic waves and how seismic waves change in their velocity to kind of image out where magma might be stored. So really the best is when you have geophysics give you a picture of where the magma might be. You have petrology give you a picture of where magma might be. An ideal situation is they overlap and you have very good constraints on where magma is stored beneath your volcano. And then if you have earthquakes and they're in that area, like, oh, hey, there's a magma storage region there. There might be cause for concern. Let's say you have earthquakes somewhere else in the edifice, that might be just like groundwater movement or something, or maybe like Mount Hood is one of the few volcanoes that has tectonic, like it's close to some tectonic faults. So you can have earthquakes at Mount Hood that are not magmatically related, and things like that. By understanding where these earthquakes are, yeah, it's literally like seismic triangulation. But you also have to know, like, okay, well, is that where magma is? It's not enough to know where the earthquake is. You also need to know, is that where the magma is? Because then that can tell us something might be going on.
is there something that happens with said magma? So like you can predict the earthquake, but is there gonna be a side effect of something that's not just like your normal earthquake? Like could you have magma leak out and do its own damage, or is it just moving underground and causing the earthquake events to happen? Or both?
Well, both. The reason why you get an eruption is just where that magma intersects the Earth's surface. So that magma can stop at any point. Magma is driven by like pressure from within the Earth. The only thing that will stop an eruption is that pressure waning. So there are lots of different reasons that a magma might stall. Most of the time, it never makes it to the surface. Most magmas don't erupt. That's how volcanoes can grow. Think about it. They kind of can grow from the inside. This magma goes in but then crystallizes. It never erupts, and that does grow the volcano from the inside out. It's just when you have the magma intersecting the Earth's surface that we call it an eruption.
So you can have the earthquake independent of there being an eruption. So monitoring
Absolutely.
gives you both the
I,
resolution of an eruption and an earthquake. So you can have two natural disasters monitored by monitoring a single volcanic region. Is that correct?
Well, earthquakes don't necessarily cause disasters. You really do need. I'm glad you mentioned. So I don't care for the term natural disasters, but that's a me thing, and that's because I feel like it's only a disaster when humans get involved. There were earthquakes long before humans and volcanoes long before humans, but were there disasters? Do we consider them disasters? Um, so that's. I'll get off my soapbox. I'm sorry.
No, that's an
Uh,
important thing to point out, right? Like it's important for ecosystem renewal too, right? So if you're looking at it just from an ecological perspective, right, it's important. And it's also like island building, like brand new islands
mhm.
being formed, new biodiversity being formed. So there's a lot of, I guess it, you're
Volcanoes and
right.
earthquakes, exactly. They're very just natural processes. They happen all the time. But to answer your question, where I think you were headed, uh, not all earthquakes will be large enough to cause significant damage to humans or human property. Just like not all volcanic eruptions will be that significant, that strong or significant. So it really just kind of depends. Like when Mauna Loa erupted in 2022, the way that Mauna Loa operates is that the eruptions start in the caldera, and then they may or may not. They may stay on the caldera, or they may go to one of the two rift zones. And so when the volcano erupted in 2022, the concern was that the magmatism would move from the caldera to the southwest rift zone, or to the south rift zone. Luckily, it moved to the North Rift Zone because the topography on the north side of the volcano is much shallower, which means that the lava won't move as fast. It won't flow as fast. You have a lot more time to move things if it becomes a danger. And there's really not a lot there. It's a bombing range for the military. There's some highways and stuff, but not a lot there in terms of like settlements and such. On the south side of the volcano, it's a very different story. And in fact, when the volcano erupted in 1950, it only took 3 hours for lava to get from the rift zone to the ocean because that side of the volcano is so steep that the lava ended up moving very, very fast. It cut people off. People were trapped in neighborhoods and had to get helicoptered out. So just depending on the wrong side of the mountain can change things. Um, eh, there's every volcano is so unique, and not all volcanoes will have the same eruption style all the time too. There are things called paroxysmal eruptions where normally like Stromboli normally has very nice eruptions. They're very cyclic, kind of like a fire fountain and a pop. People hike Stromboli, but in 2019 it had a volcanic eruption and people got hurt. So, you know, even one eruption can be different from the other. So that's why it's so important to kind of like monitor these, and you can't really forecast behavior until you see pre-eruptive signals that might give you a better idea of what that volcano might be doing. And even then, that's only good if you know what that volcano has done in the past, which is why even though a volcano might not be erupting, it's still really, really important to understand what it's behaved like in the past to anticipate what we might be able to expect in the future.
So then does studying a volcano fit into your definition of what's adequate, like monitoring, right? Because it seems the way you're explaining it to us is if you don't monitor it, you won't know. Like if you don't study it from a historical context, your monitoring will not be accurate, right? Is that is that
Yeah,
your like bonus definition of what good monitoring is? Or I
in
guess
my opinion, yes,
okay. So
but that's the USGS would consider monitoring to be only the active monitoring, but it's that monitoring can only really be put to good use and understanding if you already understand how that volcano will behave.
so what goes into the active monitoring that is, I guess, required now? Like what is it? And also you posed the question to us. We're still on the knife edge too of how many volcanoes are actually monitored.
I don't know a hard number. I really don't. I can tell you that the United States, out of any country in the world, has the most active volcanoes. We have 168, and most are in Alaska. Uh, Yellowstone is very, very, very well monitored. Mount St. Helens is very, very, very well monitored. Kilauea, Mauna Loa, very, very, very well monitored. Uh, Mount Rainier has some good monitoring. Lassen's very well understood. It's well monitored too. You can go to online. The USGS has a website, and you can look at all of the different volcanoes that are active and all the different instruments that are currently on all the different volcanoes. And this is all public information because as a U.S. taxpayer, this is what your taxes fund, right? So this is all publicly available information, and you can really see what the difference is between the different instrumentation that is put on all of these different volcanoes. And not every volcano needs to be super well monitored. You can have like so Bulent, do you know where the easternmost active volcano in the United States is?
I do not.
It's going to surprise you. Somebody in chat earlier asked like what the timelines were for an active volcano, so I want to answer that too. So an active volcano is any volcano that has either erupted within the last 10,000 years, full stop, or it has not erupted within the last 10,000 years, but we know that there's an active magmatic system beneath it. So like Yellowstone has geysers and fumaroles and things like that, and active hot magma sources. So that is also one sign for an active volcano.
That
So
second one is more like a future, like could be coming soon kind of signal, even though it hasn't happened in the past 10K.
yeah, there's
Okay,
potential. There's
gotcha.
definitely there's a hot magma body underneath there, so there is potential. And the reason we use 10,000 is because that's just like statistically, that's when it becomes most unlikely. Still can't say never, but statistically speaking, very unlikely. Um, but no, Dotsero crater is in Colorado, in western Colorado. That is the easternmost active volcano in the United States.
I've never heard of one in Colorado.
Yeah, there's an active volcano in Colorado. Just like technically speaking, like but it's very, very, very low risk, very low hazard because of the type of volcano it is and the low population that is there and how long ago it was. So it doesn't need to be have as robust instrumentation on it as like Mount St. Helens does, which is the most active volcano in the Cascade Range.
That's
So.
what, so that's what was going to be my follow-up too, was that you were saying not every one of these needs to be as monitored, and kind of what the criteria are in your eyes for putting a bunch of instrumentation on. And you kind of were answering that here too, of like, I guess,
There's
statistical
different risk
edge.
categories.
Gotcha.
So like very high risk should be very well monitored. High risk should be well monitored, but maybe not necessarily to the same extent. So when I'm talking about like things that we really need to worry about, I'm talking about those very high risk volcanoes. And no, we still don't understand how and where magma is stored beneath all of the very high risk volcanoes in the United States.
So what kind of monitoring does happen? Like, what is the instrumentation that you use? Is it something as advanced as we're shooting a beam from space and monitoring it? Is it just little, wind spinners that are hanging out on the rocks? Like, what exactly do we have? And then I guess, what would you suggest with your expertise that one should have?
So this is not my area of expertise, but this is where the USGS Cascade Volcano Observatory, the Alaska Volcano Observatory, Hawaii Volcano Observatory, or if you're in other countries, countries with active volcanoes have their own volcano observatories. And they use seismometers, which are instruments that detect earthquakes. They can also detect lahars or volcanic landslides or mudslides, because you can have those happen even when a volcano is not erupting. Like Mount Rainier, that's the biggest hazard. You don't need to have Rainier erupt for it to be very dangerous. It can have a lahar at any time. And as a result, it has the best lahar warning system in the country. So, like, Oh shoot, I got sidetracked. Oh no. Uh, what was I saying? Oh my goodness, I'm so
That
sorry.
no, that was on me. Kind of what are the monitoring systems in
Oh yeah,
place on the
sorry. Thank you.
volcanoes? Yeah.
Thank you. I'm sorry. Um, so there's seismometers and then tilt meters, which measure kind of like how the land is moving and directions. There's also GPS is used with that as well. And that can kind of tell you when the volcano is essentially breathing, right? If the ground is expanding because magma is coming in or deflating because magma is going out of the system. And then there are different types of gas monitoring equipments. So for seismometers and then the gas monitors, a technician actually goes out. So people with master's degrees in geology, these are jobs with the USGS. If you're in seismology, you get to go out. I have a call. Well, it's actually a more of like a friend through my husband's work where he works for the USGS and he goes to all these different volcanoes like in Ecuador and Guam and Indonesia and all over the world to these countries where they don't maybe have the same sorts of resources that we do scientifically here in the United States. And he makes sure that the instruments on the volcanoes are running, right? That they're tuned up, that they're calibrated well, and that they're still in operating condition, that nothing needs to be fixed and things like that. And so the same sort of instruments and that sort of like upkeep is required on our volcanoes here at home too. So those are the kinds of things that are used by the official monitoring agencies. I'm an academic. I don't have any sort of affiliation with the government or official agencies. I do independent research, and so my role is to look at the volcano's past behavior to kind of understand how those eruptions happened, maybe where magma might have been stored there. And then that information can help the active monitoring agencies to better do their job.
How did you pick the volcano that you're currently working on today? It
I
seems
can't
like
divulge my secrets in case somebody in my field is watching the stream.
okay, so it wasn't a there's like a scientific reason for picking a particular volcano to study. It's not necessarily just one where you haven't had the past effects kind of studied and highlighted.
Oh, no, no, that's basically it.
Okay, fair enough.
No,
Fair
it's
enough.
just there's a research gap. I'm just really good at keeping up on the literature.
Gotcha. That's so yeah, I was wondering like because it's you're not based where the volcano is, so you're having to travel, right, to be able to do the field studies. And so it's like, well, do you pick like a really exotic location or it isn't a gap in the knowledge? And that's a really clever way of doing it.
Yeah,
Um,
it's a gap in the knowledge. So, for in chat, if you're not sure what we mean by that, is you read through the studies to see like what is known in the science, what science is known about this site, or about in my case about this volcano, or in Belin's case about this ant species and their behavior and whatnot, and what is a question that we need to ask, and that's the question that you then try to go ask.
how did you decide like once you started doing, you transitioned in your from your master's work to these chambers to looking at more of the volcano as a whole. How did you pick, I guess, your PhD program as well? For those at home, like what was it that you were kind of looking for in terms of was it a research question? Was it a particular access to a resource? And what advice would you give folks kind of navigating if someone at home is really interested in volcanology, what to look for in these kinds of programs that you think now even in hindsight maybe could have been better or was really really good for your experience.
I mean, my advice is applicable no matter what subject you want to study. Um, so looking at like magma storage and stuff, that was my master's. I switched projects. So I did 3 years for my master's degree because I was on one project for year one and then I switched and did my second project for years 2 and 3. And I ended up kind of taking that with me and making that part of my PhD because there were questions that I had as a result of looking at these rocks that I wanted to really answer, and I felt that I could if I was given the opportunity. Um, But I ended up going to UC Santa Barbara, University of California, Santa Barbara for my PhD to work with Dr. Frank Spera, who is now retired. I was his last PhD student, so I got in just the nick of time. And the reason why I'm very glad that I got accepted. He was my top pick, and that was amazing to be able to get in. I'm so fortunate to have been able to get in there. Uh, but when I was doing this work for my master's thesis, you read the background literature, and I was trying to understand how these magmas are behaving inside the chamber and how this stuff works. And his name just kept coming up in all of these papers that I was reading. And my PhD advisor is just so freaking brilliant. He's really, one of the smartest people I've ever met in my entire life. Truly, I am so fortunate to be able to just kind of have him as a mentor. Um, but I wanted to work with him because he was developing this software called the Magma Chamber Simulator, and I thought that it'd be useful to help understand help answer the questions that I wanted to ask. And so for part of my PhD, I was lucky enough to actually help him to kind of get this thing up and running and ready to roll out to the public, help to debug it, create the user interface, do a bunch of test cases, and answer some questions about how you might be able to see what's happening to magmas by using this software. And so that was part of my PhD. And then for the rest of it, I used this tool to apply it to different magmatic systems, to chaos crags, to try to explain how these rocks kind of got their chemistry, and then also to Kilauea volcano in Hawaii to understand kind of like what was happening during a part of one of its eruptions too.
So you're
So
basically evaluating the software in real time, right? Because you can actually do the field testing, figure out how it actually happened, and then compare it to what the software predicts. Or is it even refining said software every time you do one of these like hands-on experiences?
well, it's more of like I have a hypothesis as to I think that this might be what happened in order to make the magma or the lavas this way. Then I create some models in this using this tool, and I can run them and simulate them, and they show me an idealized situation of what should theoretically happen inside of the magma chamber. Again, nature is never ideal. So this is an idealized situation, idealized examples. You gotta take it with a grain of salt, and it might not always be perfect, but a model is a model. It's better than nothing. And so if my model result is within some, close enough, then I know that I've got a pretty good handle of what's going on. I like to tell people that I'm a theoretical igneous petrologist and I serve no real world purpose as a result.
Gotcha. So it's not that you're evaluating the inputs to the model, you're generating the inputs to put into said model which will then predict maybe how it happened.
More to like to reinforce that I'm on the right path,
Cool.
if
So
that
there
makes
there
sense.
doesn't need to be live refinement of the model, I guess, is what I'm getting at. Like you're more just using it as a almost a validation technique for given the measurements that you've gotten like deep in those vents that you've gotten back to the lab.
That's a perfect way to describe it as a validation technique. Exactly.
Cool. So so VolcanoDoc, you then progressed to your postdoc work, and you said it you in our intro that it wasn't your classic postdoc, but rather it was a right place, right time, a lot of volcanoes erupting and a lot of papers done. Tell us about that. What does that entail? How did that look? What could you do? Were you on site at erupting volcanoes? Tell us all the things.
Um, so funnily enough, so no, I was not actively on site. Hang on, my camera's being funky. Um, So I was not actively on site. This eruption happened January 15th, 2022 in Tonga. This was Hunga volcano. If you've been on my stream, I haven't shut up about it in 4 years. In fact, we just resubmitted a paper on it today or yesterday. So we have paper number 3 on Tonga is in the works now. And yeah, thank you. I'm really excited. Yay, halfway to this year's tenure requirement. um,
Hey,
but
it's only March, all right? That's a big deal.
I know. Well, I'm still one down on last. Yeah, no, I'm just trying to get him out of the way and just make tenure, man. Um, but so this volcano erupted, and if you're in chat, and you don't know what I'm talking about. If you Google 2022 Tonga eruption, that'll get you there. That's all you need. This was the biggest eruption since Krakatoa in 1883. It produced the tallest known eruption plume, not recorded, but known, like reconstructed. We still haven't found one this tall. It went over halfway to space. It was 58 kilometers tall. So incredibly powerful eruption. It had so much energy so the part of the eruption, the amount of energy generated by the eruption can be split between what propagated through the solid earth, what propagated the ocean through the ocean to make a giant tsunami, and what propagated up into the atmosphere to create a land wave, which is a special type of wave that went and shook the atmosphere, went around the earth 3.5 freaking times. Like, yeah, it made a giant tsunami do stuff, make things. It was, I want to say, 60 meters at the nearest volcano, which thankfully was uninhabited. But the tsunami did kill 3 people in Peru. So all the way across the Pacific, there were deaths as a result, unfortunately. Thankfully, only 7 people died, which is, amazing considering the magnitude of this eruption. The Tongan people are very well prepared for tsunami, and they did everything perfectly. You know, there was not anything in. So what happened that caused 2022 to be so active? So this volcanic eruption, as we've come to learn, was so explosive because the vent was very, very shallow, and somehow magma and seawater got into contact, and that makes a big old boom. Magma and water don't mix well. They make very, very big explosions. So like, I think there was maybe cumulative 200 megatons of TNT's worth of explosive yield during the explosion that produced that 58 tall kilometer plume.
What's the likelihood of there being another eruption on the same site? Because presumably now that's going to be one of the things that are studied, right? Is like like you're telling us what are the things that set it off. With that knowledge, could you then predict the likelihood? And then is there an increased likelihood of it being at that site, or was that just happened to be a unique, like, one in a million kind of event?
It was not a 1 in a million. In fact, a giant caldera forming eruption at that particular volcano had happened just 1,000 years prior. But so in the near future, probably nothing. It's going to take a long time to rebuild that magma up in the reservoir, rebuild those gases, rebuild that overpressure. But this volcano had been erupting continually, like every couple years or decades here and there throughout that whole 1,000 years. So you get, some little bitty eruptions in between the real big ones. We just happened to be lucky enough to catch a real big one. So all of this stuff, because this was such a big, powerful eruption, uh, it was recorded on a lot of public information. And at the time, Belinda, you remember back in like 20, oh gosh, even, well, pre-pandemic especially, but even during the pandemic, kind of when science Twitter was just at its height, it's the golden age of science Twitter. I saw so many papers drop, like, science Twitter was where it was at. And so we would all kind of be in this little bubble following other scientists within our field. So you get an idea, who is who. It's another just networking site, right? You know who is who, who is legitimate, right? So as soon as this volcano started erupting, as soon as this eruption happened, well, the first thing was we were like, oh my God, everybody's dead because it was so powerful. And then about 20 minutes after the eruption hit hit Twitter, we saw some first kind of images of the tsunami come out of Tongatapu, which is the island where the capital is. And then the pyroclastic flows produced by the eruption completely severed the undersea internet cables, and the country was cut off from the entire world for weeks. So they were powerful enough to actually move the undersea internet cables, both the domestic and the that connected to Fiji, and then like the international one. Um, or sorry, I don't remember where the domestic. Oh, the domestic one connected all the islands, and international connected it to Fiji. But both were severed by the pyroclastic density currents. So it was all of a sudden big explosion and then no contact. So we were most concerned about the human toll, and the fact that this was, towards the end of the pandemic, that there was nothing coming out of this country, and because of COVID, there were really big concerns about coming in from the outside to this island nation, but somebody had to go to make sure what was happening. Um, and so that was always kind of like in the back of our mind until I think it was ships from New Zealand went out and made contact and were able to tell everyone was okay. Um, but I started seeing these things come out on Twitter, and I think that the eruption happened on a Saturday, so it was during stream on Sunday. This is literally in the middle of a Twitch in stream. We're looking at all this stuff. This is less than 24 hours, and I'm seeing all this data from all these like meteorologists and NASA scientists pop out, and I'm like, you know what? I'm pretty good at this stuff. I can. And so this paper that so I wrote the first paper to be published on this eruption. I was not corresponding author because the lead of the lab group wanted to be first author, which is fair. He passed away shortly after that, so whatever, that's fine. But so that was hard. That was a lot. That was probably about 2 weeks of 14-hour days continually with no breaks. So yeah, for 2.5 weeks, 14-hour days, just nonstop science, coordinating co-authors. We're all kind of doing our part, and I looked at a lot of the imagery, trying to figure out, how tall the plume had been throughout the eruptive sequence, lightning strikes and things like that, to try to get a handle on just what happened, just what the frick happened. And it was such a big eruption that we were really racing against other scientists, and we made, like, we didn't get a big journal. Ours got submitted 2 days before the guys who got published in Science were. So that's why I count myself. I wrote the first one, got submitted first. But ours was in a very small journal. We didn't make Science or Nature or nothing like that. But it was still really, really, really cool. It was still an amazing experience, and I've gotten some more publications out of it as a result. And it was just a once in a lifetime opportunity, to be able to work on such an insanely powerful eruption.
So when you're putting together that paper and writing it right after the eruption, what you're just working from home and you're just trying to find images that are piecing together the story of what happened. Is that correct?
Right. And
So
then
where do you
there's a
even look?
co-author.
Like
Oh,
where are
sorry.
you looking? What is the tools that you're like, was it Twitter? Was it just like any media?
Yeah, and then I was taking it apart frame by frame and analyzing it. And
Wow.
then we had a seismologist as a co-author, and he looked at the seismograph and the earthquake energy. We were actually able to find a new earthquake signature that had never been recorded in a volcanic eruption before. And then there was an infrasound guy. He was able to use the infrasound waves given off by the eruption to kind of pinpoint back that the eruption started at 4:02 UTC plus or minus 1 minute. So like within a minute of when the thing actually started going off. The big boom didn't happen until like 4:15 UTC. So we were able to count for 13 minutes of pre-big boom activity there. And so, I'm not the only one. Everybody in this big group is all playing our part, and we're all analyzing our own data set to just try to make number one. So that was my kind of like an informal postdoc, was as this as a member of this research group who got a couple papers out, not several, but we got two papers out, 2022, 2023, and then we've just submitted our third one.
That is insanely cool, but it also shows, just like kind of harkening back to your earlier point of how much this has to be a passion, right? Because that's like an initiative storm, right? You're like, I'm gonna do these 14-hour days and collect all the data that's out there to piece together of how this happened, and that's really really cool and really heckin' inspiring.
And I gotta, like, thank God, thank goodness for my family. Like, my family was so supportive. I couldn't have done it without, like, my husband making me dinner, recognizing, like, oh man, you're up against this deadline. And I know you and Lita, I'm sure you guys trade off and support each other when you guys are up against a deadline and stuff like that. So it's really hard to be a solo doing this. You need a lot of support from everybody to be a good scientist.
I think so. As a good scientist, I know you are busy and slammed to high heaven with being a professor, writing grants, writing papers. So we want to be respectful of your time and not keep you too much longer. I have a few more questions if that's okay.
I am happy to hang around, but I need to officially be off by 9:30 because I have to teach a 9:30 class.
You got it. You got it. We got, see, just a few more questions, and I promise. It is so cool to hear about all your experiences and how these various things work that we don't have expertise in, right? And for anyone wondering, you could always check out VolcanoDoc on our Twitch channel at VolcanoDoc on twitch.tv, which, by the way, is a great seg. How did you then get started on doing science communication, science outreach on Twitch? Why did you get started on it, and why do you continue doing it?
No, thank you for asking. So I got started because of the pandemic, as many of us did. I'm a pandemic streamer, and when things went online immediately, I was fortunate enough that, oh gosh, see, hang on, how old is my daughter? Uh, this will happen to you. This will happen to you as a parent. I think she must have been like 15, 16. So my daughter was a teenager by the time the pandemic came around, and she was like, "Oh, you should just do Twitch." And I was like, "What's that?" And so I without my daughter telling me about it, I wouldn't have even thought to come on the platform. And so I was looking around for different science streamers because I was like, well, is anybody else doing this sort of thing? And I found a couple different educational streamers. Excuse me. At the time, there was a Dr. WD40. I found Rocket Sage. Rocket Sage was the first educational streamer that I found, and she's another geologist. She doesn't really stream very much anymore, I don't think, but
Yeah,
she's
but
still
she
an
was the
active
founder. She
geologist.
was like the originator of there being any kind of
Yes.
educational anything on the platform. Yeah.
Yeah, she was a very big one of the big founders. And yeah, Ursula Mojo Spawn suggested this. But yeah, so Rocket Sage was the first science streamer that I found, and then I found some other really great communities of all different types because, as you know, Belant, you can't just, Twitch is more than just science, and you really do want to network with people outside of your kind of area to not only grow your network, but to you see what you can bring to their community and what they can bring to your community too. So I found some really great communities and started streaming just like my natural disasters class, which I was teaching a natural hazards and disasters class at the time, so I started just streaming those kind of lectures, and then I would take those VODs and cut them down, and that would be the asynchronous lecture I'd give my class. So that's kind of how I got started. And then it ended up morphing into also including my PhD research and things and doing a little microscopy, doing manuscript corrections for my PhD. And I've really just kept on streaming. Now it's kind of gone down to just, really only Sundays is all I can manage as a professor. But I stream on most Sundays. I try to do it every week, but sometimes real life does get in the way. Um, and yeah, I think that Twitch is such a great platform for this, and really it's this interactivity. It's the ability to ask questions where I can say, oh yeah, so and so in chat, I see your question, I can just answer this for you, even though this might not be as interactive with chat as many of the streams are. But there is still that interactivity between the streamer and chat that helps to drive things forward, and that is the kind of interaction that you don't get on just by watching a YouTube video, that I feel does make it more valuable for the viewers and for people in chat to be able to have access to experts, really. To you can come into my stream on Sundays and ask me how much field work is involved in volcanology. And Ella, I would say that I go out a week or two a year, and then the rest of the time I'm in the lab. So really not a lot of field work, mostly a lot of lab work, understanding, and writing. We write a lot. But I like to stream, and I stream about science because I have been lucky enough to be able to have this position and have this knowledge that I do. And one, I'm passionate. I love sharing it. I love volcanoes. They're objectively freaking cool. And how often do you get the opportunity to come across a volcano scientist and then be able to ask them a question and get a serious, real answer? That's, for most people, it's not often. And so that's really why I stream, is to be able to provide that space for people to learn, and at no cost, because you don't have to sub or anything. You can just be there, and it doesn't cost you a thing to learn, and you're getting expert information from a college professor. you know but yeah, and so I think that it's just to give an opportunity to people who wouldn't otherwise be able to access that information, because I think that that's just so important. I wouldn't, without a lot of luck and hard work, because hard work is not enough to get you there. You need a lot of luck too. And so without a lot of hard work and a lot of luck, I would not have gotten to where I am today. And so you can fall behind or fall off and maybe not make it to your dream. And that doesn't mean that you shouldn't be able to participate in cool things that you're not, that you're interested in. And so, yeah, that's why I kind of give that space. Sorry to go on a soapbox.
No, that's why we're here, and it's all stuff that I agree with and Lita agrees with. One thing you mentioned too is a lot of hard work and a lot of luck, but a lot of trials, right? And I don't know what the field is like in the geological sciences, but could you comment kind of what, because it is our Women in STEM month, what challenges did you have as a woman in science going through this, and what advice would you give to other women who are also wanting to go in the field, to kind of like either a heads up, watch out for this, or here's a bit of advice that could help you along the way?
So I have been very fortunate in that my advisors and mentors have been men who have been very supportive of females and been very just like insistent upon them being present and valued. Um, that is definitely not always the case. And in fact, geology is a very young science, where so Ursula Mojo in chat, she's also another earth scientist. She and I got our PhDs together. I went to grad school with her. We both have our PhDs from the same institution, actually. And she's a climate scientist too. And there was a professor at our university. That's how young my science is. And that's really with plate tectonics where we kind of got our modern understand our foundation of what has now become our modern understanding of the earth. So our field is less than 100 years. Our modern field as we know it is less than 100 years old. And
Is
yeah, it
that
got
is
us out
that
water.
Is that due to technological breakthroughs that were needed to establish the field? Was it just a happenstance that someone like what? Why is it so new? It seems like it should be something that should be, a far older in terms of what's how it's being studied, right? Because the Earth is there.
Right, but we didn't. So there were a lot of hypotheses about like the plates moving and why things happen. This is Alfred Wegener's continental drift hypothesis. And he had a lot of evidence to support it, but he couldn't explain why things happened. And with the Earth, you really need that mechanism that explains the why. It's not enough to just make observations and come up with a hypothesis. You have to explain how things can happen. And so that why didn't really come around until like the late 50s, early 60s, and with the kind of plate tectonic revolution. And so Dr. Tanya Atwater was the first female geologist on a research vessel, um, and which is amazing that she's a professor emeritus where I got my PhD. Like that's how young our science is. Um, and so I've been very lucky to have good female role models. But I can tell you that as a female scientist out on my own, it is definitely not easy. I struggle with something as simple as just getting somebody to call me doctor. Like, uh, it is I am the only female professor in the department, and the male professors don't seem to have a problem with students calling them doctor. But it is like, yeah, yeah. People don't want to call me doctor. They call me miss. Like, I'm married. I don't even get a missus, man. And yeah, so that's even just something as basic as just being addressed with the title that I've earned is hard to get that recognition. I, I'm very glad to be a scientist in the 2020s now, because women are more supported than we were, especially, even 20 years ago. Um, you hear horror stories about female scientists getting the smaller lab space. So even though, I may struggle with some of my colleagues and my students wanting to give me the recognition that I deserve, I've been, like I said, very fortunate to have good mentors and advisors who have been very supportive of women. The department chair, when I was hired, very, very supportive of women. But you still like,
Uh-oh. Oh, there she is. We got her back.
I'm so sorry. I don't know what happened.
No, it's
Um,
okay. It's this really heavy topic, and all of a sudden, like, oh no, please come back.
I'm sorry. Oh no, now I forgot what I was going to say. Oh no. Uh,
Still, all the challenges having to go through, like the students not having the right level
yeah,
of recognition, but then also presumably, I mean, in the field, do you experience that as well?
like when I'm out in the field, I usually go, by myself or with colleagues. I've never really had a problem with that. Oh, but I know what I was gonna say. But like, I don't look like a normal scientist. I have piercings. I am heavily, not heavily, but I'm moderately tattooed. I have facial piercings. I say hella. you know. Um, I am sometimes not a family friendly, and so I defy what people's expectations are of what a scientist should be and is, which I actually like, kind of. It's kind of fun. Uh, but at the same time, it's really infuriating to have somebody come into my lab looking for an appointment with me and talk to me and tell me, like, no, I'm looking for this person. And I'm like, yeah, that's me. This is my lab. That's why I have the authority to talk to you. So it can really be nice and not nice to not look stereotypical. But it's gotten a lot better for women, I will say, but we still face something, like I said, as simple as just being recognized.
I'd like to highlight something that you said, which was, oh, I don't look like a scientist. And I think that you being on this platform, you being a professor, you traveling, you going to these conferences kind of will helps more people connect with being a scientist, right? Like there's not this stereotypical image of an old white dude as having to be a scientist. So my big like kind of rounding out question to you is you do look like a scientist. You are a scientist. How does it feel to be a woman in science, but not also that being an inspiration for the next generation?
Ooh, that's actually the most difficult question because I still have quite a lot of imposter syndrome. Um, I'm not quite comfortable being looked up to yet. I still don't really feel like that guy. And I had this conversation with my grad students actually. We went and did lab work at another university and taught them, brought them out, taught them how to do digestions of rocks and stuff and run an ICP-MS and get their data. And now we're dealing with it. What they were telling me about how they look up to me, and I'm just like, I don't know. Please stop saying that. It makes me uncomfortable because I really do feel like I'm just everybody else. I don't feel like there's anything special about me. I feel like I'm just like a normal person. I just also happen to be a scientist and a professor and a volcano helper. So I don't know. I'm very honored that people have that opinion, and I'm privileged and thankful. I just don't know that I'm quite comfortable with it yet because it's just new, you know?
I'd like to personally highlight that I don't think it's new. I think it's something that you've been inspiring people for many years as you've been, going, getting the GED, the master undergrad, the masters, the doctorate, the postdoc work. I feel like at each one of those steps, sharing that with us today is inspirational to someone, which means you've been inspiring people in your entire journey, is the way I like to view it. And I know that you've inspired many of us in the science community just with your story, and you just always finding the good fight and streaming, bringing the educational content to folks, and just being you. And so I really, really appreciate that.
Thank you. I really appreciate it. Because those words are, really nice to hear, especially when you have those bad days, when you're banging your forehead against the computer screen because your code won't compile and you feel like a failure. It really does help to have people have faith in you. It makes you a little worried about letting them down sometimes, but it helps that for them to have faith in you.
There's that, like you said, the imposter syndrome and the fear of letdown is always a big thing. But it's not a fear. Is where can people find you? What would you so as we're rounding out, Doc, thank you again just for your time, for sharing your story with us, your experiences and your expertise. And obviously not enough. We couldn't get into everything, which is all the more reason why people should go check out you. Where can
Yeah.
people find things Dr. Volcano Doc related? Where should people go? What time should people go? Please plug all the things.
Oh, yeah. No, thank you for having me on. I really appreciate the opportunity and the platform, and I think that this series is great. I am thankful for you for running it and highlighting all of the amazing women in STEAM that are on the platform. So I stream on Sundays, typically in the afternoon, uh, Central Time. Um, it's a little bit variable, but like afternoon Central between like 2 and 4 is typically when I'll start. Um, yeah, so Sunday afternoons on Twitch. I'm kind of active. I check Blue Sky, but we have a Discord that I'm typically active in. So the Discord channel, and then Sundays on Twitch, and I lurk around in a lot of chats, pop in every now and then when I can. A lot of lurking because I'm usually doing stuff and working and things like that. But yeah, and then if you and I have a website too. If I can I put it in chat?
You can do
Um,
whatever you want. It'll be in the show notes for everyone listening at home too.
it's vdocscicom, well .com, but yeah, so vdocsci, that's my website, and it's very bare bones right now, but there's a contact me if you're interested in a collaboration or want to read more about my research, get some sweet swag about magma propagation, things like that. And I'm really hoping to be able to raise money for a gimbal and like the mic set and things, because I'm going back out to the field this summer. I won't be able to live stream from the field, like at least from the way up. I'm going to try inside the vent because my undergrad actually was able, okay, very unsafely. And I definitely chewed his tuchus for this, but he totally scurried to the top of this obsidian spire because the vent is just like these big obsidian spires and magma just comes up. So he scrambles to the top of this and FaceTimed his buddy. So I know that there is enough internet to FaceTime somebody from inside the, well, at least on top of the spire of the vent of this volcano. So if I can, I'm going to try. But at the very least, I'd really like to be able to record the footage and stuff and like hiking and kind of what we do field work wise, to be able to show people on stream and maybe post a YouTube video to give you guys an idea of what it's like. It's mostly we just walk around on lava and hit rocks with hammers.
Listen, field work is incredible, and it's something that, we at home, we don't know what it looks like. Right? We just
Which
like
is why I
you
want to share it with you.
exactly, like you telling us and you talking about it and you sharing that, like that's I think it harkens back, like you said, as kids, when you and I were kids, did we have access to a professor volcanologist who would teach us and go through what they do? No. So again, you are that pioneer that is doing that. And VolcanoDoc, thank you again for your time today, for
Thank
what
you
you
for
do
having
and
me.
just everything. Thank you so much.
I really appreciate it. I'll probably lurk around in chat for a little bit. I've never shoveled lava into a bucket, but yeah, I did see my first eruption about a year ago, which was very nice. But I have to teach a class in 12 hours and 3 minutes.
So look, we
So
cut it perfectly then, right?
thank you. Yeah.
Thank you
Thank
very
you so
much
much
again,
for having me
VolcanoDoc.
on, Balint. I really appreciate you and everything that you and Lita do for the platform and for science education and SciComm.
Thank you so much, Doc. Guys, make sure to go follow Dr. VolcanoDoc, her website, her Twitch page. She might even get a throne page, and you can donate to her gimbal and her audio set and far more. We can get her hooked up on those IRL streams as well.
That would be cool. Alrighty. Have a wonderful evening, y'all. Have a lovely evening.
Have a lovely evening to you too, Doc.
Science is for everyone, all backgrounds, all ages, all genders, and all walks of life deserve an education. Come be one of us.